Okay. Now I guess I can get the camera to focus. Okay, so rules for logarithms. Now there are easy explanations of these rules, and I'm probably going to talk about them a little bit. Make sure I can see all of this board. My H and M ran together there, but you know what I'm saying. Okay. Now, the log of A times B is the log of A plus the log of B. And I'm not necessarily using the same letters your book uses. Different books use different letters, and I don't pay much attention to that. Okay, the two biggest ones are the log of A times B is the log of A plus the log of B, and the log of A to the n equals n times the log of A. These are related to rules for exponents in a way that I'll probably address, but let's just take the rules. Now, there's another rule for the log of A divided by B, but if you combine these laws or these rules, you get that rule. So an unnecessary rule is that the log of A divided by B is a log of A minus the log of B. Okay. If you divide A by B, it's like A times B to the -1, which would be the log of A plus a log of B raised to the -1. But B raised to the -1 would be -1 times log B, so you get this. So it's worth understanding that and thinking about it just to get a better handle on the rules. But those are the rules, okay? Now, a couple of false rules. I'll put a watch out here. Watch out. The log of A plus B, you're used to the distributive law. It looks like that ought to distribute to give you log of A plus a log of B, but it's not so. The log is not a linear operator. If it was a linear function, then, f of A plus B would equal f of A plus f of B, but only if f is linear, meaning it has a straight line graph. Log doesn't have a straight line graph. This won't happen, okay? The graph isn't linear, so that's not so. And also, log of A to the n is not the log of A raised to the nth power. Again, that just doesn't work, okay? So these are things you got to watch out for because it's very easy to do this and easy enough to do this. So those are pitfalls. Okay, well, how does this apply? Well, let's just look at And we go to log base 2 because we can easily understand the base 2 log. So log base 2 of x squared equals 3. Well, that means by this rule, 2 times the log of x equals 3. Log base 2. So log base 2 of x is 3/2. So in terms of what you've already done for homework, you understand that x is going to be 2 raised to the 3/2. Just changing this to exponential form. Okay? And that's about 2.828 because that's just 2 times the square root of 2. So that's straightforward. Okay? Let's take another example. Let's say we have I don't want to use a negative, we'll use a positive. Okay, base 2 logs. Now here we have a sum of 2 logs with the same base. And I haven't put bases on these. Let me go ahead and do that. This applies no matter what the base of the log is. So it could be base 2, it could be base 10, could be a natural log, base E. So in this case, we have a base 2 log again. Base 2 logs on both sides are in this form. So now we know that this can be written as log base 2 of x squared multiplied by 2x plus 3 equals 2. So that x squared multiplied by two x plus 3 equals 2 to the second power. That's a cubic equation. You have a 2 over here. Now that would lead you to the equation two x cubed plus 3x squared minus 4 equals 0. Now, it's unlikely that that equation is going to factor. You can use the rational roots theorem, which I talked about a little bit, and you can test to see if 1 is a solution, but it isn't. 2 plus 3 is 5, minus 4 doesn't give you 0, okay? You could see if 2 is a solution. Well, clearly not. Maybe negative 2 is a solution. That would give you negative 16 plus 12 minus 4. Well, if it was plus 4, it would actually be a solution, but it isn't. So you can investigate solutions. If you can find solutions, you can do a long division and use the process to solve the equation. Chances are it's not going to work because I didn't make up the numbers in order to make it work, okay? Now the numbers are small and simple, so there's a chance it'll work, but probably not. So what you might do is sketch a graph or create a graph. You won't know exactly where the zeros are, but you can try some graphical solution to at least approximate the zeros. that doesn't change the fact that we've converted this equation to a simple polynomial equation. And we have methods for attempting the solution. And there are methods for approximating the solution. Okay. So with that, I'm just going to look at the homework for this section and just kind of go through that and give you some examples of the sorts of things you'll look at. But what I've already shown you is a good bit of it. And I'm going to kind of go, well, okay, you see how these rules can be useful for solving logarithmic equations. So now let's just look at how you would simplify one side of a logarithmic equation. Let's say you have the log to the base 3 of 4x squared. And the square should go over here so you can see it. Minus log to the base 3 of 5x to the 9th minus 3. Okay. We can combine these expressions into a single log. Okay. This was equal then to log to the base 3 of 4x squared. And I can make that notation a little better. What happened to my other cloth? On the floor. Takes me a minute to get down there. Okay. So log to the base 3 of this divided by this. Okay, and this uses the fact that log of A over B is log of A minus log B. So we have the log of this divided by this. Okay, let's look the other way. Let's expand the log of, could be any product. Okay, so let's say we expand the log of x to the 4th. Let's put a 3 out in front of here. X to the 4th, y to the 7th, z to the negative 5th. Okay, well, we're going to use the rule that says a log of AB equals log of A plus log of B. And also, we've got exponents in some of these things. Log of A to the n equals n log of A. Okay, so we get if I group these terms where the first two factors are grouped and the second two factors are grouped, turns out this is going to be the most efficient way to do this. We see that the log of this times this is the log of 3x to the fourth plus the log of y to the seventh z to the negative fifth. Just using this rule where a is your 3x to the fourth and b is your y to the seventh, z to the negative fifth. Now I could have grouped it otherwise. I might have grouped the x to the fourth, y to the seventh, z to the negative fifth, and the log of 3. So I'd have the log of 3 plus the log of x to the fourth, y to the seventh, z to the negative fifth. It's arbitrary how I do this, but the way I've done it is maybe the more efficient way to do it because I need fewer steps. And you can think about how to minimize your number of steps. Basically, if you divide a long expression in half and then divide each of those expressions in half or close to being in half, it's a little quicker to get through the problem. Okay. Anyway, log of 3x to the fourth is clearly then log 3 plus the log of x to the fourth. This is then going to be the log of y to the seventh plus the log of z to the negative fifth. Well, that's got it down into 4 separate terms, but now at least 3 of these terms have exponents, so we can apply the second rule and we get log of 3 plus 4 times the log of x plus 7 times the log of y minus 5 times the log of z. So if, with a little practice, we learn to recognize these situations where these rules apply, it becomes fairly straightforward to break the thing down in a few steps and obtain the final result. Now, once you have a lot of experience with this, you can see, well, it's going to be, and you can actually do this, we're going to have the log of 3 and the log of x to the fourth and the log of y to the seventh and the log of z to the negative fifth. It's actually safe to skip this step and go directly to this step. I recommend that you do this step a few times until you're really convinced that you can just skip from this all the way down to this without having to do this. And then once you have this, you can write the rest of it out. And once you get used to it, you can actually pretty much just skip from here down to here. Because you're going to have the log of 3, and that's going to be it. You're going to have the log of x to the fourth, and that's going to be 4 times the log of x. And log of y to the seventh is going to give you 7 log y. And similarly with the z term. So you can kind of skip steps, but at first I recommend that you fill in all the steps just to make sure you see how everything breaks down. Okay. Well, I'm going to turn off this camera for a second. And I'm going to actually close it up till I need it again, which won't be long, but I'm trying to maintain the charge as long as possible. I have a charger, but this camera is sitting precariously on my keyboard. I haven't yet created a way to securely mount the camera. And when it's sitting up there, I don't want it connected to the cord because it'd be easy to pull it off. Okay. So once we understand these rules, and they aren't hard to understand. They just take a little practice, and be sure you avoid the pitfalls that I warned you about. Then we can go right back to solving equations. So let's take the equation. I'm going to use base 2 logs again because they're fairly easy to calculate with. Okay, here's an equation. And excuse me for a second while where do I put, well, I can't find anything. Now everything's going to fall apart. Okay, big great April Fool's joke. If I did that and that thing fell and it knocked something else over, and pretty soon everything in the room collapsed. And maybe the ceiling collapsed around me. I don't want it to collapse on me. So I need to work on that one. I probably won't have time to do it today, maybe next year. And if I do, I'll invite you to observe. Okay. So anyhow, let me get serious again and open the camera and aim it. Okay. It's really convenient that my keyboard sits at an angle that allows me to do this real easily. And then I'm going to start the video, but it just moved the camera dog on it. So we'll come over here and hope that I'm still aimed. And the video is blurry right now, but it'll be okay. Okay, now here's the equation now. We want to solve this equation. So we use the rules that we have, and I'm not going to quote the rules this time. Just log of this plus a log of this equals a log of this times this. So this tells me log base 2 of the quantity x plus 2 times 3x minus 5 equals 4. Well, that was easy, okay? And now it's easy to convert this to exponential form. And 2 to the 4th, of course, is 16. And now, what kind of an equation do we have? Well, should be clear, this is a quadratic equation. So this is a quadratic equation. If this was equal to 0, then we would simply solve it by saying, well, x is -2 or x is 5/3, okay? But we're not going to get a 0 over here. Actually, yeah, but you can't get 0 over here, okay? There's no power of 2 that's equal to 0. So your log can't be 0. So you're always going to have a number over here when this happens, which means you're going to have to expand your quadratic expression on the left and then subtract this so you get it in standard form. I'm going to go through the details because people want to skip them. And I know that's not a problem for you, but other people could be viewing this. Okay, so we distribute x times this plus 2 times this. I want to emphasize this. That F word thing doesn't apply here. It does, but I dislike it so much that I don't use it. And then we distribute through here. 3x squared minus 5x plus 6x minus 10 equals 16. And you know that now we're going to combine our terms and we're going to have just a simple quadratic equation. And we're going to be able to test the discriminant to see if we can solve it exactly, see if it's factorable. The equation is going to end up being 3x squared plus x minus 26 equals 0. Now, the only way we can factor 26 is with 2 and 13, or 26 and 1. And there's no hope that numbers like that are going to give us something that, that factors. But just to be sure, the discriminant is b squared minus 4ac, which goes under your radical, which is going to be nine squared minus 4 times negative 26 times 3. That's going to be 81. Let's see, that's going to be 104, and 3 times 104 is 312, which is 393. 400 is a perfect square, 361 is a perfect square. This isn't a perfect square, so you got to use the quadratic formula. I'm not going to waste time here. With something that should be second nature. Plug these A, B, and C into the quadratic formula, and you get your solutions in terms of a square root of 393. And that's 3 times 131. You're not going to factor a square out of that. Okay. So it's going to be an ugly looking thing, but you're going to easily get decimal approximations to the solutions as close as you want them. And that's going to be sufficient for most applications. Okay, so there we have another example of an equation. Now we did an earlier example where we got a polynomial equation. And that's probably pretty hopeless to solve using exact numbers. This one, we know for sure doesn't give you exact numbers, okay? The cubic equation we had before, you can use a rational roots theorem to verify that there are no rational solutions. Okay, and now let me take another quick look and see if there's anything that's coming up that I think anybody should have any problem with. Yeah, there is another example that I would not necessarily have thought of. Okay, here's one. We don't have just a number over here, you have a log. And the log could be to any base, and it's not really going to matter what the base is in this case. It's not going to make any difference at all. Okay. Okay, so if we combine what we have over here, well, we can write this as log of 2x. We could combine these right away, but let's just write it out this way. Log of 2x plus the log of x minus 4 minus the log of negative 5x equals 0. Then we can write this as the log of 2x times x minus 4 yeah, okay, over negative 5x equals 0. Well, any log, any expression whose log equals 0, that expression has to be 1, because the only power of any base, that the zero power of any base is 1. So this tells us that negative 2x times x minus 4 over 5x equals 1. Now, if your log is base b, you know that we'd have this equal to b to the 0. No matter what b is, b to the 0 is 1. Okay, so let me just make a note here. B to the 0 equals 1 for any base. So now our equation becomes minus 2x times x minus 4, multiplying both sides by 5x. So now negative 2x squared plus 8x equals 5x, but I'm just going to bring the 5x back over here so that negative 2x squared plus 3x equals 0. It's a quadratic, but it's really easy to factor. And when you can factor in an obvious way, it's a good idea to do that. So we get x times negative 2x plus 3 equals 0. And now we can use the 0 property of multiplication. If you multiply two things, get 0, that means at least one of them has to be 0. So we get x equals 0, or negative 2x plus 3 equals 0. So our solution set is 0. And if we solve this, we get x equals 3/2. So this equation looked like it might turn out kind of nasty. Turns out to be pretty easy. Okay. You know, if you understand these examples, you're in good shape for the homework that'll be due at the time of our next class. I'm going to go on and talk about some other topics that are coming up, just to give you a little head start. And now it says charge the battery pack. So I had 61 minutes. And in less than 40 minutes, I ran out of battery. Okay, well, I'm not going to be able to use the great camera. So I'm just hoping, maybe I'll risk setting the thing. If there's a way I can secure that. I'm going to pause the video here and play with this for just a second. It won't take long.
Okay. The quality isn't really bad as it is.
Resume the recording. And take the shroud off my camera. There it is. It's all blurry, but it'll focus itself. It already has. Okay. Now I wish I'd washed more boards because I'm kind of running out, but not too badly. Okay, so let's just look at the graph. You know, use base 2 logarithmic functions because base 10 gets out of hand too quickly. Higher bases are inconvenient, but we know what to do with them, okay? So we're going to graph log 2 of 2x minus 4. Okay. Now, I want to do this by transformations. Okay, well, for any function, f of 2x minus 4 equals f of 2 multiplied by x minus 2. And that is an f of k times x minus h. And don't want to use k just because we usually use that for the vertical shift. So I'm going to use c. Kind of forget what your book uses. I haven't talked much about horizontal compressions, although you've done it and you've done it successfully. C equals 2, that's a horizontal compression. H equals 2, which is the horizontal shift. So we take our graph of the base 2 logarithm of function. And I'm going to graph this without comment. Actually, I probably will comment for the sake of people who still don't understand the basic functions. Okay, well, here's our graph. And if we understand the basic functions and how we invert them, it's very easy to see that this is the graph. Just to remind people, I'm going to write it over here in the margins, so to speak. Our 2 to the x function, we have 1/4, 1/2, 1, 2, 4 for our standard x values. And for the log 2 of x function, we just simply invert the tables. And that's it. So without further comment, and if you don't understand this, and you certainly do, but anybody who doesn't understand this, go back to the basic function scheme. Make sure you understand it. So we have this graph. Now, if we want to get the graph of log base 2 of 2x minus 4, well, for any function, f of 2x minus 4, you have a horizontal compression factor of 2 and a horizontal shift of 2. So the horizontal compression, which we have to do before the shift, because the compression involves a multiplication and the shift involves an addition or subtraction. And by the order of operations, we have to do the multiplication first. And that transfers over without going through the details of how it transfers. But you can think about that. Okay, so we have to move every point twice as close to the x-axis. So this point moves to here. 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 It's getting hard to mark these accurately. And this point moves in really close to the x-axis. Okay, so horizontal compression, every point becomes twice as close to the y-axis. Now that's because twice as close because your compression is by factor 2. If this was 3, they'd become 3 times as close. If C was 1/4, then you'd have a horizontal expansion by factor 4. You move 4 times as far away. In any case, here is the resulting graph. And this is the graph of y equals log 2 of 2x. Now we shift this h units in the x direction, because when you replace x by x minus h, to get the same y value, your x has to be h units bigger. To make x minus h as big as x would have been, it's got to be h units bigger because you're subtracting the h. Ouch. That was nothing, just a surprise. Okay. My pet cobra sunk its fangs into my calf. No, remember, this is my basement. Anything is possible. Okay. Now we're going to do the horizontal shift. So we got a horizontal shift of 2 units. Okay. So now we need horizontal shift plus 2. Well, 2 units is this far, right? So I can even draw my 2 unit vector here. And I apply this 2 unit horizontal vector to every one of these points. So I'm going to try to be careful here. Well, I'm not going to manage it. But we move this point over 2 units. We move this point over 2 units. We move this point over 2 units. And, you know, I kind of knew it when I did it. I should have made this 2 unit vector a different color to avoid confusion. I was worried about that, but not worried enough. Okay, so we take this point and move it over 2 units. We're going to put it about here. And we move this point over 2 units. Well, that's at 1. That's at 1. It's going to move it over to 3. No, it's going to move it over to 1.5. And then this will move it over to 3. And I moved it a little too far. But then we get the idea that the graph is going to look like this. Okay. So our red vector here now, the word vector, as my linear algebra students or my multivariable calculus students from last semester will tell you, has all kinds of profound connotations in mathematics. We're not going to worry about those connotations. The basic idea of a vector is it's something that moves something. So this arrow just indicates movement by 2 units in the horizontal direction. And it should be obvious how that corresponds and how that was used up here. So now we have the graph of y equals log base 2 of 2x minus 4. Now, if there's a color I haven't used yellow, so I put something in here. Don't have a lot of room, but what's the domain? Okay, I got some space here, so I'm just going to write out the domain. Well, 2x minus 4 has to be greater than 0 because you can't apply a log to something that's less than 0 because the exponential function can't be less than 0, okay? And make sure you understand that connection, that the domain 2x minus 4 is greater than 0. So x has to be greater than 2. Now, I could have done that originally, but I wanted to work this through. And we see that since this vector has length 2, and any point on the graph of the log function is going to be to the right of the x-axis, no matter how close it is, it's still a little bit to the right. That means the line x equals 2 is your vertical asymptote, okay? In other words, all these points on the log graph are to the right of the y-axis where x equals 0. So when we move it 2 units, they'll all be to the right of x equals 2. And they get as close as you wish to get to the y-axis, to the line x equals 0. So in other words, they're asymptotic to the line x equals 0. So this will have to be asymptotic to the line x equals 2. So I'm not going to draw it real dark, but I'm going to say that, so here's where x equals 2, and yeah, my graph isn't perfect, but x equals 2 is your vertical asymptote. So the graph of any logarithmic function can be constructed. Now, this one has a horizontal compression and a horizontal shift. But we could put a number out in front here, and that would then give us a vertical stretch. And we could add a number onto the end here, which would give us a vertical shift, okay? So we can do all those things with the logarithm function. And all of those things could occur. There's another way to construct this graph. And if I've got a bit of clean board available, I'm going to do that. Okay, I'm going to have to move a few of these. But I'm going to keep this one. Yeah, I think that'll stay there. And I'm going to take these two and move them down here. Okay. Oh boy. Keep your mind on the task. Okay. Again, Zoom doesn't handle smudges well, so I'm going to be careful about that. Okay, y equals log base 2 of 2x minus 4. Incidentally, I should blame that on Zoom. Zoom, some combination of Zoom and my internet service provider causes smudges to be bad. So I don't know who to blame and what share of the blame each might have. But it's not my computer because everything is clear as a bell on the screen I'm looking at. Okay, then another way to graph this. Well, same factorization where I got my horizontal compression and my horizontal shift. But of course, this equals the log base 2 of 2 plus the log base 2 of x minus 2. By the multiplication gives you addition rule, okay? And this is just going to be a horizontal shift of the log function. And then we just raise it up, log base 2 of 2 units. What's log base 2 of 2? It's 1. So if we just take this graph, shift it over 2 units, the original white graph, shift it over 2 units and raise it 1 unit, we should get exactly the same graph. Now it's going to look like heck, but I'm going to go ahead and sketch where these points would be because they're easy to locate. So my white graph would transform by moving it 2 units to the right to here, and then here, and then here, and then we'd have to go 2 more units to get here. Okay, now it doesn't look quite right because I didn't have a great scale on it. But this would be log base 2 of x minus 2. And then if I raise every one of these points 1 unit, well, how am I going to say it? This point will become this point. This point will become this point, and so forth. I don't want to try to do that, but we raise it. Okay, we raise this 1 unit, and the graph ends up going through this point and this point, and this point. So I'm going to have to draw it. I can't draw it here so it's visible. But again, we shift this graph to the right 2 units and then raise it 1 unit, and it's going to coincide with the graph that we got here. So let's just go ahead and construct that. I didn't realize that I was going to do this when I started. Made a bigger graph here and planned it out. Okay. So we have, again, a graph of the base 2 log. And as we did before, we move the graph to the right 2 units. Well, there's our 2 unit vector. And moving it to the right, I use a different color here, we end up with these points. So the green graph is the log of x minus 2. And then we move it upward 1 unit. So if we move upward 1 unit, this point goes up to here. This point goes up to here. This point goes up to here. This point, which I didn't locate very well, but it goes up to here. And we see that this graph is steeper than either one of these. It's like, well, it's the same effect as we would have by horizontally compressing it. So if you compare this graph with this graph, you see that it's in the same relation to the original log graph as this one is to this log graph. It's at least plausible. Now you have to kind of construct that yourself to see that it's really so, but it works out very nicely. If you do it on a very accurate set of axes and a large graph, so you can do these points that are close to the asymptote, you see that it works. Also, the asymptote of this graph is going to be, again, at x equals 2. So it's kind of a neat little application of one of the rules for logarithms, where we can construct the graph of this function in either of two ways that end up being equivalent. So it's always kind of neat when two unexpected things end up being equivalent. Very satisfying to a mathematician, to somebody who has no desire to be a mathematician. I'm not sure how fascinating it actually is, but I hope you found it at least halfway interesting. Okay, I'm going to stop the recording.
Interesting. Yes, I wouldn't even think about it, but